So this part 310, which is going to be the normal stresses in a beam, is one of the two things. So one is we need to know the normal stress, which comes because of bending moment and shear force. We need to know the shear stress, which comes from due to M and V. So this is where it fits in. So we talked about shear force and bending moment. And we talked about Morse circle. So shear force bending moment gives us M and V. Morse circle gives us sigma tau. Okay. Let us do it this way. Think of this as a block. Okay. So here we have loads. And out comes from this comes the M and V. And for the Morse circle, we have sigma x, sigma y, tau xy, and of course the incline. And then it gives us the sigma and tau at that incline. But then there's a piece missing, which is how is M and V related to sigma x, sigma y, and tau xy. And that's the block we're going to talk about now. So it's this thing which is going to tell us about what is that thing which goes into this box, which gives us sigma x, sigma y, tau xy, so that we can use that in the Morse circle. And there's another piece. So this one is going to give us sigma x, sigma y, and then there's another piece which is to come in 311, which is on transverse stress or tau xy. So once you know 310, 311, we'll have that block, and that actually completes the whole thing. So we can go from the left side to the right side. And if you want to know more about this, this is where you apply transverse stress. Okay, so this, maybe I should just complete this. So this goes in, gives me sigma tau, and this is where our failure theories sit. Right? So that would be what we did in chapter 2. Right? So once you know this, you can design find things like the dimensions, D, thickness, and so on. So this is where the design sits. Design is about designing one of the parts of designing, once you fix the material, is to figure out what's the size of the, what's the radius of the, or diameter of the shaft and so on. And that comes because of stresses or some failure theory, but the failure theory requires stresses at different inclines, which comes from the Morse circle, which comes from the, what we're going to do right now, and then which comes from the bending moment diagram. This is basically completes that loop which we were after. Okay, so this will make us more illuminated about what exactly can be used to find the shear force, the normal and shear stress. Okay, so that's sort of the introduction. Let's get to this particular section on normal stresses. Okay, so in this case, what we'll do is we'll only consider, so we will consider only bending moments and assume that shear stress is 0. Okay, and so that's kind of required because the equations which are developed are based on this assumption. Now, you'll say, why is this useful? This seems to be not very useful because here m is uh, uh, m is non-zero, but v is zero. But rarely do we see a case when both of these things are true, right? M is non-zero and v is zero. It turns out that if you look at the way you design things, is that when the bending moment is maximum, that's where things will fail due to, in this case, normal stress. That's where you'll see that the shear stress is actually zero. And I'll just show it to you why that's true in a bit. But you typically take points where the stress is maximum as to be points at which you want to specifically look at the diameters, because that's where things will fail. So here are cases where this is true. Okay, these are just some of the examples. And there are other ones too, but let's take these three ones. So one of them is if you have a specimen or a beam which is loaded in this fashion, P, right? And these forces are symmetric. Okay, this is actually known as a 4-point bending specimen. It's a very famous setup used to test for failure of material by pure bending moment. And that's because if you look at the shear force and bending moment diagram, the shear force diagram will look something like this. So the left side will have a positive shear, and then it'll all be zero. And then when it reaches the other P, it'll be a negative shear force. So it's zero here. So it's P here, and then of course, minus P here. If you look at the bending moment diagram, it'll be zero on the edges. It'll reach a maximum at the point where the P is applied. It'll stay constant and then go down back to zero. Turns out this is P times A. So something like this would perfectly fit our theory here, because in this section, specifically in this section, M is non-zero, but P is zero. That is, shear force is zero. So this is a case where it will fit our theory. It's also interesting to see that when the bending moment M is maximum, which it is in the midsection, the shear force is actually zero. Okay, so this just happens to be the case most of the time, that when the bending moment is maximum, the shear force is zero. And it's actually universally true. I'll show you now why that happens. The second case, which you'll see this is true, is if you have a beam which is subjected to a cantilever beam subjected to pure moment. So in this case, if you draw the shear force is, there's no external force applied here. So the shear force is actually zero for the entire, it's all zero. Then let's draw the bending moment diagram. That is, this one is going to have a constant bending moment, M. Whatever the M is applied, let's call it M0. That's difficult to relate when M is supposed to be the general bending moment. So let's call it M0. So this is M0 on the y-axis. So this is our diagram. So again, M is non-zero. But the shear force V is zero. Okay, so here again, our theory will be applied. Okay, so I said this fact is true for almost all cases we'll be considering here. and I'll just show you why it's true. So the claim is maximum normal stress occurs when M is maximum. Okay, this statement, well, where did it come from? Well, I will derive expressions in a bit, okay? But just for now, just believe me that the maximum normal stress occurs when M is maximum, okay? If M is maximum, then we know that the shear stress G is dm dx. So that's universally true. It's always true. So if M is maximum, then how do you find the maximum of a quantity? Well, you take that quantity, you differentiate with respect to x, you take the derivative equal to 0, and that's how you get the maximum or minimum, right? So you do dm dx equals 0, right? But if dm dx equals 0, then clearly v should be 0. So this implies v is 0 when M is maximum. So this is a result which comes purely from calculus. So we're good. So most of the time, what I'm going to show you is true, which is when you see that the M is maximum, V is 0. And then the equations, which I'm going to show you in a bit, which is this part, is always true. So once you've made a case for that, let's go on looking at what is the effect of the moment M on a beam. And we'll develop the equations and then use those equations to find the stress. Okay, so as I said, consider a beam in pure bending. Okay, which is another way of saying that the shear stress is 0. So let's take a beam. Okay, and then load it up with a moment M. If you apply a moment M, it will bend in a shape like this. Right? It'll be sort of convex. Okay, there would be a layer in the middle which is actually unaffected. So there'll be the layers on top are under compression. Because they are shortening and the layers below are in tension. And so if some parts are shortening and some parts are lengthening down, there should be an axis or a layer where there is no stretching or compression. So that layer is called the neutral layer. So this layer shown in red, not stretched, okay, is known as the neutral layer. Put here to be correct, not stretched or compressed. And then this axis are called the neutral axis. So I can as well draw a line like this. This axis is the neutral axis. Okay, the axis which harbors the neutral layer, or the layer where there's no stretching or compression when a beam is subjected to pure bending. Okay, so now with that, let's see how we can go from M to stress, because that's what we are trying to do here, right? So once we know stress, then we can use Mohr's circle. So I'm going to show you how to relate M with normal stress sigma. So we have this beam. I hopefully convinced you that there is a layer which is unstretched, called the neutral layer. Okay, now let's consider a layer which is, let's say, just below the neutral layer, and let's call that CD. And let's say the distance of that layer from the neutral axis is y. Can say that this distance, which is now, this is a beam along the x-axis, so let's call that delta x, and this is just a small element of the beam. Okay, so now we apply a moment m, and because of the moment m, this beam is going to be bent. I'm really drawing it exaggerated. So that layer is in red is a neutral layer, a neutral axis, and that's unstretched. But then the layer CD, which is the distance y, is going to be stretched. Let's call that C prime D prime. So then if you extend these lines, they should intersect at some point. Let's say call it O, and that's this angle with theta. Okay. This has to be true. The bending is severe, then that radius is, let's call this as it's the radius from here all the way to the neutral layer. If it stretches by a lot, then that R is going to be small. If the bending is not that severe, then that R is going to be very large, right? Okay, so we have R here, we have Y, it's going to be unchanged. This is still Y. Okay, so once we have that, now the question is, what's CD? CD is, you can see over here on the left side, it is delta x, right? But delta x is also the length of the unstretched portion of the stretched beam, right? So it's basically this delta x. Okay, you can see if you remember simple trigonometry, that arc length is r times theta. Okay, where this is clearly, it's this thing which I'm of interest. And then we have C prime D prime, which is now this and this, which is the stretched length at a distance y from the neutral axis. It's going to be, since it's at a distance of r plus y from the center, its arc length is r plus y times theta. Okay, just because of that distance. So now we can find the strain. The strain is defined as the net change in length, so C prime D prime minus CD divided by the original length, so it's CD. So C prime D prime is R plus Y times theta minus CD is R times theta divided by CD, so it's R theta. So if you do the math on that, it just works out to be y divided by r. It's not a function of theta anymore. It's just a function of the distance y and the radius. Okay, so we got the strains. Now it's not very hard to go to the stress because we know that the strain and stress are related. So the strain is sigma times sigma divided by E, where E is the Young's modulus. And so we can write epsilon equals sigma divided by E equals our just expression which you just derived, y divided by r. And so if you want to find sigma from these two, it's simply y divided by r times E. Okay, can highlight that. And what we notice here is the interesting thing that sigma, which is the normal stress, is proportional to y. So again, what's y? If you take this beam as a neutral axis, y is the distance from the neutral axis. So bigger the y, the bigger is the stress. So the stress is going to be the maximum over here, right? It will be tension. So assuming it's bent this way, it's going to be tension over here, max tension here, max compression here. So people like to draw this as follows. There's zero stress. It's draw the cross section. It'll be, and then if you think this as positive, then that's maximum tension. It decrease, go to zero, and then it will be negative, maximum here. Something like this. Sigma max. And then sigma min. It's actually compression. And it's just zero here. Zero stress on figuring out the neutral axis. So what I'm going to do is I'm going to derive an expression for the net force in the same beam, which is subject to bending moment. So if you have the beam, which is now bent, okay, and then this cross section is like so. So I'm going to try to find an expression for the net force in the horizontal direction. Okay, there is a stress sigma here. And of course, it's going to be compression in one side and tension on the other side. But nevertheless, that force can be found as sigma times dA, where dA is the cross-sectional area. Or delta A. dA is fine, delta A is fine. I think it is perhaps the same. Delta, yeah. I use delta, but you can use D, that's fine. Okay, so once you have this expression, let's try to replace the value of sigma from this expression. Call it something else. Let's call it 1, Roman 1. And so we sub that in. Y divided by R times E times delta A. And this comes from 1. So if you want to find the net force, again, the force is this one, delta F integral. Then we need to take the integral across that surface. So I'm going to take, move things around. E divided by I, Ry delta A, but E is a constant. The radius of curvature, which is 1 divided by R, is also a constant. So we can remove that out. So we are left with integral Y delta A. Now, we know that when there's pure bending, the force in the horizontal direction is 0. So this quantity here is 0, which means that so since is 0, okay, so we have a peculiar relation which says that the integral of y dA is 0. When y dA, the integral of y dA is 0, then we can be certain that what we have is for the neutral axis is actually the centroidal axis. The neutral axis is the centroidal axis. So this implies, this expression implies that the neutral axis is the centroidal. What it means is if you have a cross section, all you need to do is find the centroid of that cross section. The centroid is going to be the neutral axis. So for centroid, for regular geometries like square or circle, is going to pass right through the center, across the diameter for a circle, and across the half the width or half the width and half the height of a rectangle. But for a section which is say T, it's less obvious. But then you need to find the centroid of that section, and that centroid is going to be the neutral axis. So we'll do this again when we do some problems. Centroidal. That's the first insight. The second insight is going to come when we take the bending moment, right? So the net moment can draw the beam. That's the beam. It's subject to a moment m. And in this case, what we're doing here is taking a small, well, we're taking the cross-section area, and in the cross-section area, there is the centroid. We are taking a small element here, delta A. And let's say that this element is at a distance of y. Okay, so we wrote down an expression for force is E divided by R y delta A. So if you want to find the moment, which is dm, and since this force is acting in this direction, F, all I need to do is take dF, multiply with the moment arm. So this is finding the net moment about the centroidal axis, the neutral axis, and then sum this across. So m is the integral delta m, which is integral delta fy. But delta f is something we already have here. So let's call that 2. Sub that in this expression, E divided by R y delta A. So I just subbed in delta f here. And then I'm left with y. So I plug that in. And so now I need to simplify this. What I'm going to do is pull out E divided by R because that's constant. And I have y squared delta A. Now the moment is not 0. The moment is something which is finite, right? Because this whole theory is based on a beam which is subjected to a pure moment m. Now this I is the moment of inertia about it's the area moment of inertia inertia about the neutral axis, okay, which by the way is the centroidal axis. So I can write this as m equals E divided by R times I. We also know that, so something which we derived right here. Not here. We also derived an expression for sigma. Okay, there it is. Sigma is y divided by r times c. I'm just going to rewrite that. Sigma equals y divided by r times e. So what I'm going to do is try to write all these expressions in one single equation, 3 and 4. So from 3 and 4, and this is the only expression you ought to sort of know in order to solve problems. I find m divided by I, so that's that, equals E divided by R. So this can you see from, you can see from 3, right? But that E divided by R is also sigma divided by Y. So that's like the expression which I think is the only expression you need to know in this section in order to solve problems. That is, if you know M, which is typically comes from the bending moment diagram, you can find sigma now because you know the section modulus, which you can compute. You know the y. Y is the distance from the neutral axis. So for a given distance, so if you want to find the stress on the surface, then you'll put y equals whatever, breadth divided by 2 or height divided by 2. And then E is a constant and R is typically unknown, which you can also find using this. So you can tell how much this beam has bent due to the moment M. Okay, so with this, let's just see how to apply these formulas and solve problems. Okay, by the way, I should just tell you about I, a little bit more about I. So if you have a cross section, so I drew a rectangle, and we're typically trying to find I here, and let's say that this is B and this is H, then I is B H cube divided by 12. Okay, so this is something which I'm not expecting you to remember. It's something which I'll provide to you. There is a table in the book which gives you the inertia, moment of inertia about different sections. So that's for a rectangle. There's something else for a circle and so on. So in this case, also, if you want to find max sigma, right, when does sigma attain a max value, then it would be when y achieves the max value. So at y equals h divided by 2, because remember, we're measuring y from the neutral axis. So if you want to find max sigma, all you do is you take this expression and you plug in the value of y, where y is h divided by 2, and that will give you the maximum stress. So that stress is going to be compressive on one face, it's going to be tensile on the other face, depending on how the M is applied.